Welcome back to our next video on non-commutative geometry and non-associative extensions through naive class theory. In this section, we're going to cover differential graded algebras as well as smooth fiber bundles. First, we're going to cover graded commutativity. We'll start off with a variation on commutativity called antisymmetry or anti-commutativity. The exterior product is a bilinear associative operation that is an example of something that generates this anti-symmetric behavior. But in traditional notions of multiplication, usually we consider the following commutation to hold between common objects, such that when I multiply a times b, it's implied that that's the same thing as multiplying b times a, such that a times a is equal to a squared. But for the exterior product of differential one forms, such as dx, dy, d theta, or other functions such as f of x dx, f of x dy, etc., we end up with the case of anti-commutativity. So that for the differential forms omega and eta, which are one forms, their exterior product, also called the wedge product, is equal to minus eta wedge omega, such that omega wedge itself is equal to 0. And this is a special case of graded commutativity. This specific variation of it, however, but specifically between one forms, is the heart of the exterior algebra of differential one forms. So now let's consider differential graded algebras. For differential k-forms, which can include anything such as scalars, smooth functions, dx, combinations of differentials such as dx, dy, where often a wedge is implied between them, or differential three forms such as dr, d theta, d phi, and polar coordinates, etc., the general rule of graded commutativity is given by the following. So for differential k-forms, omega and eta, their wedge product is given by -1 to the power of the multiplication of their degrees times eta wedge omega. And so the commutativity we are familiar with, where a times b equals b times a, for standard products is just a special case of this situation where the degree of either omega or eta is even. A differential graded algebra over a field, such as the real or complex numbers, is given by two components. One, a graded algebra that I'm calling a with this degree symbol, and this degree symbol is to remind us that we're taking a direct sum over the integers of n powers of this algebra A. And that's the grading of the algebra. So multiplication respects the following grading. If we have objects a to the I times a to the j, it's assumed that this is either a subset of or is directly equal to a to the power of I plus j. And two, we have a differential map D that maps a to the n to a to the n plus 1 that satisfies a second order nilpotency property. So the differential of the differential is equal to 0. And the graded Leibniz rule is obeyed. So if I take the differential of a product a and b, that gives me the differential of a times b plus -1 to the degree of a times the differential of b. Now let's consider a specific differential graded algebra called the exterior algebra of differential forms. The exterior algebra of differential forms on a differentiable manifold that we're calling M is a unique example of a differential graded algebra, and it's given by the following two components. The space of differential k-forms over a differentiable manifold. And we grade it very similarly from k equals 0 to infinity in this case, and it's just the space of differential forms specifically instead of just an arbitrary algebra. And the exterior product given by this wedge endows the space of differential k-forms on that manifold with the structure of a graded commutative algebra as expressed before. But a differential D that maps the differential k-forms to the differential k plus 1 forms on the manifold is called the exterior derivative, and this also satisfies the second order nilpotency condition, such that the exterior of the exterior is equal to 0. And the graded Leibniz rule is obeyed once again, although in terms of the exterior product. So if we have the exterior derivative of the exterior product between omega and eta, this is equal to the exterior derivative of omega, wedge eta, plus -1 to the degree of the differential k-form omega times omega wedge the exterior derivative of eta. For our differentiable manifold, each local section of coordinates hosts a vector field that we'll call this curly looking v, and that yields a tangent vector at every point of the manifold through this following summation. So it's a summation over all I of all of these contravariant vectors with these partial derivatives in respect to that contravariant basis. And the union of all tangent spaces at all points forms an object called the tangent bundle. And this is the tangent bundle to the manifold, denoted by Tm. It assigns to each point x of that manifold a tangent space T sub x of m, and that T sub x of m is referred to as the tangent space at point x of the manifold M. And the set of all smooth vector fields is then referred to as the space of sections of the tangent bundle. And our vector field V is indeed an element. So gamma of Tm is the smooth space of sections of the tangent bundle on the manifold. But dual to this, however, is the space of sections for the cotangent bundle, denoted T star M. And this gives us the space of all differential one-forms. But to obtain the space of all differential k-forms, more generally, we grade the cotangent bundle inside of that space through the kth power of the exterior product. And so the space of sections of the kth exterior power of the cotangent bundle is the space of all k-forms on the manifold. Recalling that the tangent bundle Tm assigns to each point x of the manifold a tangent space T sub x of m, we can state that the cotangent bundle T star m then assigns to each point x of the manifold a cotangent space T star sub x m that is dual to the tangent space at a point x on the manifold. And the tangent and cotangent spaces at each point x of the manifold are called fibers of their corresponding exterior power bundles. So the fiber of the kth exterior power of the tangent bundle at a point x is just given by the kth exterior power of the tangent space at that point x of the manifold. And then, as such, the fiber of the kth exterior power of the cotangent bundle at x is given by the kth exterior power of the cotangent space at the point x of the manifold. It is then correct to say that the tangent space at a point x and the cotangent space at a point x of those manifolds are the fibers of the tangent and cotangent bundles, respectively. And thus, the tangent bundle and its dual, the cotangent bundle, are both examples of smooth fiber bundles. And the space of all smooth sections is then a global section of what is called a sheaf of differential graded algebras over the manifold. Now we'll get more specific with the space of differential one-forms. And this space that we discovered prior is spanned by the elements of the following form for each local section. We'll call this V star, where star refers to the dual of the vector space. In this case, this is a covector space or a dual vector space. And this sums over all I of the covariant vectors with the exterior derivative. The exterior derivatives can now be recognized as the dual bases of the partial derivatives at every point of the manifold. We can state this formally by saying that the canonical dual pairing of the exterior derivative with the partial derivative operator equals the Kronecker delta function. And this is essentially a generalization of the identity matrix. When we sum over its trace, this gives us back the dimension of the manifold. We can consider now a function f, which is an element of the space of smooth functions on the manifold. We declare this formally by saying that f is an element of C infinity of m, where C infinity of m is the algebra of infinitely differentiable functions on the manifold. This algebra is the structure sheaf of the smooth manifold and acts as the canonical ring of functions for differential geometry. The role of the exterior derivative d on a function f, which is an element of this algebra of infinitely differentiable functions, is to yield a differential one form. So we sum over all I of the partial derivative of f in respect to x with the exterior derivative. And if our base field is the real numbers, a one-dimensional field if you will, we obtain the following result. The exterior derivative of f is just the partial derivative of f in respect to x times the exterior derivative of x. In the three-dimensional Euclidean vector space called R3, we have the following. Notice we don't multiply any of the exterior derivatives together, nor any of the sum differentials themselves. So these are all differential one forms, and the sum of all these differential one forms is also a differential one form. And we call that df, the exterior derivative of the function f. And this goes on for arbitrary dimensions. But finally, for differential k-forms, we can generalize the fundamental theorem of calculus for n-dimensional manifolds through the action of integration on forms. And this is encapsulated most notably by the Stokes-Cartan theorem. This states that the integral of the exterior derivative of a k-form over the whole manifold is equal to the integral of the k-form itself over the manifold's boundary. That is, the integral of a k-form is always related to at least one integral of a k-1 form in the form of a boundary term, and this is regardless of the dimension. The exterior derivative is then recognized as the opposite of the boundary of integration. So differential forms truly are objects that are meant to be integrated over. And a first course in single variable calculus, at least for most people, is secretly the study of differential one forms in terms of a single coordinate variable. It is the study of forms f of x dx that are elements of the space of differential one forms on the real numbers, where f itself is an element of the algebra of n arbitrarily differentiable smooth functions on the real numbers for n greater than or equal to 0. Such that the integral ranging from a to b of f of x dx is equal to the anti-derived function evaluated at b minus the anti-derived function evaluated at a. This summarizes the initial information we need for differential graded algebras in order to move forward, as much of our future work will be to consider the consequences when non-commutativity takes over. And in general, we will be moving away from manifolds entirely, replacing their structures with algebras that feature more degrees of freedom.